Hello, Geometry. This is Chapter 6, Lesson 3. So we finished Lesson 2, which dealt with two little properties of triangles and going from the vertex to the points that are opposited. Okay, so angle bisectors and perpendicular bisectors were the two that we did there. And those concurrent lines come to a point of concurrency, and there are certain properties that happen at that point of concurrency, such as a circumcircle or the inscribed circle, an incenter. So a circumcenter, which created a circle around it, there we go, that's what I was trying to say, or the incenter, which created a circle on the inside of the triangle. So 6.3 introduces two more types of relationships between the vertices and the sides, and that's going to be a median. And whenever you see the word median, I want you to think about kind of the word middle. Median is kind of the middle. And altitudes, you got to think about the height, and I also want you to think about a 90-degree angle. Okay, so medians and altitudes are the two things we're working with here. So when you do a median, what you have to have here is this point has to be the midpoint of segment AC. That has to be a midpoint of segment AC, and then you connect to the vertex to that point, and you have what we call a median. Okay, same thing with here. D has to be a midpoint of segment BC, and then you connect those two, you have a median. Okay, and they meet right here together. Okay, so, and when we look at altitudes, an altitude has to form a 90-degree angle, so it has to be perpendicular. So our slope is perpendicular to the slope of BC. Okay, to whatever the slope of BC is, the slope of this has to be perpendicular and it goes through A. So that's how we create an altitude here. So when I go to Desmos, I'm creating these. There we go. Let's get a new one here. So I get any sort of triangle. Boom, boom. I like the grid on here for some reason. Show that grid. So if I want to do a median, I have to select a side, and then I can find a midpoint. And then my segment would go, my median seg point would go right there to there. And we can check the median. What you have to do is you have to put segments over this part and this part. And then you can select that specific thing, and you can find the length. Oops, not the whole length. Hang on, put that back on there. Okay, something's not working. But it would be, this would be 2.57 as well down here. Well, now I did it, didn't I? Sorry, let's get this back here. So that's how you can just select the side, select the midpoint, and you're going to get a point of concurrency at where these all meet. So you have a point of concurrency right there. That point is called a centroid. And that centroid has a unique property here. So some of our vocabulary before we get to the centroid here. The median of a triangle, this is going to be a segment that connects a vertex, that's our corner, to the midpoint of its opposite side. To the midpoint of its opposite side. A centroid, this is the point of concurrency for the medians. That is a point of concurrency for the medians. the altitude of a triangle, this is going to be a segment that goes from a vertex that is perpendicular, segment that goes from a vertex that is perpendicular to its opposite side. And the orthocenter, that is what we call the point of concurrency for the altitudes. Point of concurrency for the altitudes. So, unique things about the centroid. Centroid theorem here. The centroid, which is going to be your medians, so we notice this is going to be a midpoint, this is a midpoint, and this is a midpoint. The centroid of a triangle is 2/3 of the distance from each vertex to the midpoint of the opposite side. So it's 2/3. So it's going to be splitting things into thirds here. So if P, it's what it's saying here is P is 2/3 of the distance from B to F. So let's say F is 5. If that makes P to F 5, that would make this 10. It's going to be twice that distance. Okay? So the longer side is twice the distance, the shorter side is half of what the other one is. That would be 2/3, because the total length from B to F would equal 15. Okay? And if you take 15 divided by 3, you're going to get 5, and that's going to be the short distance. And if you take this, 5 times 2 equals 10, this is going to be the long distance. Okay? The whole thing's 15. So let's say CD, what about CD? Let's say that is 18. So from C to D, that is 18. What are the lengths of the two individual parts? Well, since this is a centroid, you're going to take 18 divided by 3. You're going to get 6. That's going to be the shorter of the two sides. So it looks like that would be from P to D. That would be 6. Okay. So that equals P to D. And then we're going to take 6 times 2, that is 12, and that is going to be C to P. So that's 12 right there. Let's do one more, go to blue. So AE, what should AE be? Give me a number, any number. Preferably divisible by 3. So that looks like it might be the longest side. Let's go 24. Okay, so A to E is 24. You can take 24 divided by 3, we get 8. So H has to be this distance right here. Shortest distance. So that's P to E. 8 times 2 is 16, and that is going to be A to P. So you kind of see how that relationship works. Now the other thing that's cool about the centroid, it is the center of mass. So if you were to cut out this triangle and you would attach a string right where the centroid is and hang it, that triangle should hang balanced, perfectly balanced. So if you're making if you think of the mobiles that maybe babies would look at that swing around, those can be created by different shapes. Finding the centroid of those shapes would make sure that mobile stays balanced. So the centroid is significant because it is the center of mass. The other thing it does is it creates three equal triangles of area. So it's the center of mass, and also creates 3 triangles of equal area. 3 triangles of equal area. So I'm going to go back to Desmos and pull up a diagram that I have made already for the centroid. I want you to see these triangles here. So here's my centroid, which is the center of mass. Make it bigger for you. And you see the centroid is on the medians, but if I create 3 triangles that are different colors here, green, the red, and the orange, 3 triangles formed by the medians, that creates 3 triangles of equal area. The numbers there is the area of the triangle. Okay, so the label is the area. So no matter how I move this around, that centroid, wherever that goes, always creates 3 triangles in there that are of equal area. That's part of how it makes a center of mass. Now you also notice I cannot get that centroid out of the shape. Okay, it is always inside the shape there. So centroid will never be on the triangle and it will never be outside the triangle. Centroid will always be inside the triangle. Things like that might be good extra notes to write down. Okay? So you don't always have to write down just what I write. If I say something else you think it might be useful or helpful, go ahead and write that down. Okay, so these questions that deal with the centroid might be something like this. Point P is a centroid of triangle LMN. Find PN and QP. So they say QN is 33. So they want us to find PN. That looks to be the long side. And they want us to find QP. So I'm going to take 33 divided by 3, I get 11. That should be your short side. That would be QP, that would be 11. PN is 2 times that, because that's 2x, so that's x, and that's 2x. That makes that 2/3 of the distance. So that would be 22. So PN is 22, QP is 11. Okay, QN is 45, that makes that x, that's 2x. Divide by 3, I'm going to get 15. So x is 15, so QP is 15, and PN is going to be 30, twice that amount. Okay, so if you can get number 3 done, come back and check. Okay, x should be 13, so QP should be 13, and PN should be 26, twice that amount. So that's some unique things about the centroid. Okay, we'll come back to that. Let's talk about orthocenter on this side. Orthocenter is the point of concurrency for the altitudes. The altitudes form a 90-degree angle. What happens with the orthocenter? I'm going back to Desmos here. Let's make a new one to show you how to make one real quick. So here's my triangle. If I want an altitude, you can go to More Tools. You want a perpendicular line. Click a side to set the slope, and then click the point, the vertex opposite, and you're going to get an altitude that way. So you can keep going that side. There, there, there. And I want to do some of this stuff in class with you also. Okay, so there's my orthocenter. And you notice if I move things around, the orthocenter can be on the triangle, it can be outside the triangle. Okay, so orthocenter is one that can float around all different places. If you have a right triangle, it shows up right on the vertex, right where the 90-degree angle is. Okay, so the orthocenter can be made that way. Kind of the unique thing that happens with the orthocenter is that if you reflect the orthocenter over any one of the sides of the triangle, it's going to land on the circle that is formed by the circumcenter. Okay, so watch this. So these little orange dots here, these are the reflections of this orthocenter over this side, and it lands here. So no matter what kind of triangle I have, if it's a right triangle, they all meet together there. Coincidence. Okay, that's what happened with Venus and Jupiter. Those planets came together really close to form a big star a few weeks ago. Okay, so that's kind of what's one of the unique traits about the orthocenter. Again, you reflect it over any of the sides. So if I take the orthocenter, reflect it over this side, it's going to land right there. So a reflection of the orthocenter over any side of the triangle will land on the circle formed by the circumcenter. And keep in mind the orthocenter can be inside, on, or outside the triangle. Okay, orthocenter can be in, it can be inside, on, or outside. Okay, the centroid can only be inside. Centroid can just be inside. There it goes. It's kind of like the circumcenter can be inside, on, or outside. The incenter can just be inside. Okay, a few more questions here, then some lovely diagrams. My handy dandy ruler. Okay, we have another centroid. Think of the 1/3, 2/3 rule. Page 178. They want CD and CE. CD and CE. So DE is 7. So they're telling us this is 7. They want CD, where CD is alongside, so that has to be 14. It has to be twice the length. And then CE, this is 14. That has to be 21. Now I do want to point out here the 3 triangles that would have the same area. This area would have to match this area, which will have to match that area. Okay, so those are the 3 areas that would have to be the same, caused by the centroid right there. DE is 12, so that's 12. That makes CD. CD is alongside. That's 2 times it. That's 24. And CE would then be 12 plus 24. That's 36. Okay. So that's fairly straightforward. Again, color in which triangles, where are the triangles that have the same area. And you go ahead and pause it, color those in, so you can get those lines in the right way. So if I follow B to D to A, here's one triangle. Okay, it's formed by the 2 vertices and the centroid. So here's one side. Just go up to the centroid. Oops, need different color there. And then this side right here. Okay, so those would all form the same things. Okay, here we go. Find the coordinates of the centroid of the triangle with the given vertices. So let's get these mapped out. I have -2, 1, and 4 as my x values. So let's put my y-axis right there. And I have -1, 8, and -1. So I got to go pretty high. I'm not going very low. So we'll put that there. So A is -2, -1. B is 1, 8, 2, 3, 4, 5, 6, 7, 8. And C is 4, -1. 1, 2, 3, 4, -1. Okay, so the centroid. Centroid deals with the medians. So I need the midpoints. I want the midpoints. And again, the third, you need 2 of them. The third one is kind of your check to make sure it works. So we're just going to work with 2 of them here. I'm going to start with things that are horizontal and vertical. So 1, 2, 3, 4, 5, 6 is that length. So 1, 2, 3. Again, you can use your midpoint formula. So that's going straight up or down for that median. Okay, so for this side, if I use B and C, if I use a formula, I have to take 1 plus 4 divided by 2, so that's going to give me 2.5. And then I have to go 8 plus -1 divided by 2, that's going to give me 3.5. So 2.5 and 3.5. So 1, 2.5, and 1, 2, 3.5. Okay, so it'd be right there. So that would be my centroid right there. It looks to be at 1, 2. 1, 2. And again, you can check it. This other side would probably be right there and right there. You go through. Okay? So there's a centroid. Next one. -5, -3, -1. All on the left side of the y-axis. So let's put this clear over here. 4, -2, and 4. little bit higher than we're going lower. 4s are greater than 2, so let's put it right there. So negative 5, 4, 1, 2, 3, 4, 5, 1, 2, 3, 4, there's D. Negative 3, negative 2, there's E, and negative 1, 4. There's F. It's like another isosceles triangle. Right triangles would be easy. I don't want to make it too easy for us. Okay, horizontal side, my median is right there. So this is also an altitude then, since it's an isosceles triangle. So if I want to find the median of this side, that has a difference of 2. So it's going to be right there. Okay, because there has to be 1 unit in between them. Again, you can use the formula for E and F. Negative 3 plus negative 1 divided by 2 is negative 2. So at negative 2, it'd be right there. Negative 2, 1 if you check the y values. Connect that to the opposite side. That puts my centroid right there. Go back to your origin. 1, 2, 3, 1, 2. So negative 3, 2. Negative 3, 2. Uno mas. Okay, we got 8, 20. Ooh, 8, 20, and 8. We don't have 20 grids on here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have enough to count by 2s. So 8, 20, and 8, I'm going to put the y-axis way over here. 7, 5, and 3. It can be down here. So this one's counting by 2s, this one we're going to count by 1s. So x is counting by 2s, y is going to be counting by 1s. So 8, 7 is 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. There's 8, 8, 7, 25, 10, 12, 14, 16, 18, 20, 2, 3, 4, 5, and then 8, 3, 1, 2, 3. So L, K, J. What do you know? Another isosceles triangle. That surprised me too. I thought it'd be different. So, get the easy one. The middle of this side is right here. Okay. Now the other way you can probably think about this is remembering the centroid is 2/3 of the way from the vertex to this side right here. So if I get this one right here, this length is 1, 2, 3, 4, 5, 6. So the length is 6. If I divide it by 2, I get if I divide it by 3, I get 2. So I'm doing basically what we're doing on this side. Okay, if you know the entire length, you can divide it by 3, and you can get the shorter side, take that times 2, and you get the longer side. That's another way to think about this, do it this, okay? So this is 6 units long, divided by 2, that means your orthocenter has to be 2 units right there, 2 units along the way. Which would put us at 2, 4, 6, 8, 10, 12, 1, 2, 3, 4, 5. 12, 5. Okay, we probably could have checked that on all of these. Notice this length is also 6, so divided by 3, you get 2. So from the side, it should be 2 units. This length is 1, 2, 3, 4, 5, 6, 7, 8, 9. Divided by 3 is 3, so it's 3 units up from that side. Okay, let's work on the orthocenter. This is the altitude. So we have 3, 3, and 11. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Just fits. We're going to put it right here. And 6, 0, 0. So don't mind zeros be down there, so we'll go right there. So 11, 0, I know it's going to be right there. That's Z. 3, 6, 1, 2, 3, 1, 2, 3, 4, 5, 6, and 3, 0. Yay! Right triangle. You will like right triangles when you have this. Because guess where your orthocenter then is? Okay? The orthocenter is the vertex. So orthocenter is at the right angle for every right triangle. Makes this easy. That'd be 3, 0. 3, 0. There's your orthocenter. Now, if they make all three of these right triangles, they're making it way too easy on you. You're getting off easy with it. -4, 1, and 6. Let's put that right. 1, 2, 3, 4. Let's put it right there. And -4, 1, -4. So we don't have to go up very high. So -4, -4. 1, 2, 3, 4. It's L, 1, 1. There's M. And 6, -4. 1, 2, 3, 4, 5, 6. There's N. That looks like a right angle. If that's a right angle, let's check our slopes. So this slope is up 1 over 1, so this slope is 1. This slope is down 1 over 1, that slope is 1. We do have a right triangle, so which vertex would be our orthocenter? That would be on M. So that would be 1, 1. Okay? So if you remember, for the circumcenter, when you had a right triangle, the circumcenter occurred on the hypotenuse. That would make sense because of the orthocenter. If you reflect it over either of these sides, it reflects onto itself. So the circumscribed circle has to be going through the vertex of a 90-degree angle. So that's going to be a proof when you get to circles that if you have a circle that goes through the diameter, if this is the diameter, it's going to be a 90-degree angle up there. Anyway, that's extra. And I'm not going to charge you for that amount. Okay, last one, I believe. Let's see. 3, 11, and 9. So we know 11, these are 11 across, so let's put that y-axis clear over there. 4, 4, and -2. I'm going to go in the middle, maybe a little bit lower. Whoa, we didn't draw that well. 1, 2, 3, 1, 2, 3, 4. 11, 4, and 9, -2. Okay, do we have another right triangle? No, it doesn't look like it, does it? No, I don't think so. Okay, so let's get this side first, this horizontal side. It has to be perpendicular. It has to be perpendicular to each side. So that makes this side right there. There's 1 altitude. So what I would do is this side right here has a slope of up 3 over 1. So M is 3 over 1. Up 3 over 1, up 3 over 1. A perpendicular slope would be -1/3. So just like what we did with linear equations, I would go to this point, and let's go down 1 over 3. Down 1 over 3. Okay. Let's draw that line. Doesn't seem to be matching up much with a nice point there. I forgot a piece of instruction there. Okay, let's check this one. Let's make sure we got this right. Let's check this slope. This slope is going... Let's just go here. So it's going down 1, 2, 3, 4, 5, 6. 2, 3, 4, 5. This is -6/5 is the slope of this line. So let's go to the opposite side. Our perpendicular slope would be +5, 6. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. That would create a positive slope. Okay, and our orthocenter is definitely on the inside. That's something we're forgetting here, telling whether it's inside on or outside. This one was on, this one was on. Okay, so finding those coordinates, this requires a little bit of algebra here because you would have to have a system of equations basically. We know, where'd that other sheet go? we know that x has to, we have a vertical line here at 9, so we know that x has to equal 9. So we need to find out what is this y value where it's meeting right here. So we'd have to find a linear equation and then plug x into that and find out what our y value is when that is x is 9. So I know this red line has a slope of negative 1/3, and it goes to the point 3, 4. So I can use point slope form. I could go y minus 4 equals negative 1/3 times x minus 3. And let's plug in 9 for x. If we want to, let's clean this up. Y minus 4 equals negative 1/3 x. Negative 1/3 times negative 3 is a positive 1, so plus 1. So I get y equals negative 1/3 x plus 5. Plus 5 if you add the 4 over. So if I put this 9 in here, I'd get negative 1/3 times 9, which is negative 3. Negative 3 plus 5 should equal 2. Well, maybe your graph did better than mine, because I am getting that these should meet at 9, 2, and that is not where they're meeting. Maybe 1, 2, 3, 4, 5, 6, 7, 8. That is 8. 8, 8, 8, not 9. You probably counted me. 8, 9, 10. Oh, everything's off then. I'm sorry, I goofed this one up, didn't I? Maybe you did it right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That only has 10. I thought we had 11 on here. This one bigger? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, we threw it off again. But again, 11. That would work. That didn't really mess anything up because you still have your right angle there. Okay, make sure you count correctly. That'll be good. Okay, so we're not going to fix that one. The final one I do want to look at is when you have to go outside, when you have an obtuse triangle. And that is when your orthocenter is going to be outside. And you're going to have to extend some sides for this to work. So let's say we have negative 3, 2, 3, 4, and 8, 0. Okay, we're going to graph these 3 points here. Negative 3, 2, 3, 4, and 8, 0. 2, 3. And I'll make sure I count correctly this time. 2, 3. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9. 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Alright, so when you're looking for this orthocenter here, this side down here, this is the easiest one, because this slope is going down 1, 2, 3, let's see, we're going down 2, and over 1, 2, 4, 5, 6, 7, 8, 9, 10, 11. Negative 2/11ths, so our perpendicular slope should be 11 over 2. So from here, I'm going down 11, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and over 2 to get a positive slope. Line those up. There's one altitude. It does look like a right angle. Now these others can get a little tricky because you'll have to extend this side out a little bit. So this slope here is up to and over 1, 2, 3, 4, 5, 6. So that is 2 over 6, which is 1/3. So your perpendicular slope from this point, here's your side, this point which is opposite should be negative 3. So 1, 2, 3 over 1, 1, 2, 3 over 1. You notice you're going off the outside the triangle. Your orthocenter is going to be outside the triangle. So we get to come back in this triangle. I'm going to line this up. I'm just going to put dashed marks to show that I'm extending the side. So we say extend the side. Extend the side. So we can still, I'm going to draw this farther. Oops, that should have been green. And here's red. So our orthocenter should be out there. Let's practice this one more. This slope, this is going 1, 2, 3, 4, down 4, and 1, 2, 3, 4, 5. So this slope is negative 4/5. Our perpendicular slope would be 5 over 4, positive 5 over 4. I was looking at this line, opposite would be this one. So positive 5, 1, 2, 3, 4, 5, 1, 2, 3, 4. 1, 2, 3, 4, 5, 1, 2, 3, 4. Now we don't know what specific point that is because I made up these values, but they all go through right there. That is your orthocenter. That would be on the that's where the orthocenter is. If you reflect that over these lines of the triangle, it would land on the circumcenter. The circumscribed circle. There we go. A lot of vocabulary, a lot of words here. A lot of information with this. Take your time, try to remember it, make sure you're thinking about each question, not just rushing through them and getting them done as fast as possible, so you can remember this when it comes time for the quizzes and tests. So good work. We'll see you in class.